I'm feeling a lot better now that I took that break. Got some cardio in. I didn't do my hike. I went did some echo bike cardio, but got my blood pumping. I feel a lot better, a lot more motivated here. So let's pick up where we left off. Let's see how the linker uses this algorithm to relocate the references in our example program. In figure 7.1, figure 7.11 shows the disassembled code from main.o. So we got our main.o code and relocation entries from main.o. The original C code is in figure 7.1. Okay, so we got, so this is pre-relocation then, right? And it's annotated with these relocation entries, which usually aren't in the disassembly. But A and F, EDI, because EDI points to the array, and call Q needs to be updated to where the function is. The function sum is. So figure 7.11 shows that the simple code from the main.o is generated from the GNU objjump tool. Oh, okay. So that objjump actually does show relocations. Let's test that out. Let's go into build here, and we'll just say objjump on main.o, and we want to do a disassembly. Well, that doesn't seem to be right. I think they added their own relocation entries, unless there's like a flag for that. Let's see it in the text here. Let's do man obj dump relocation R. Let's try that. dr. Hey, look at that. We got our relocations. Yeah, if we did this on like main itself, of course there's not going to be any relocation entries because it's statically linked. Okay. So I didn't know that. I didn't know that you can ask for relocations in the output. Disassembly. Okay. Let's go back to the reading. The main function references two global symbols, array and sum. For each reference, the assembler has generated a relocation entry, which is displayed on the following line. Cite station 2 here. Recall that relocation entries and instructions are actually stored in different sections of the object file. The object tool displays them together for convenience. Okay, cool. The relocation entries tell the linker that the reference to sum should be relocated using a 32-bit PC relative address, and the reference to array should be relocated using a 32-bit absolute address. Next two sections detail how the linker relocates these references. Okay. Relocating PC relative references. Line 6, figure 7.11, function main calls the sum function, which is defined in module sum.o. The call instruction begins the section offset 0xe and consists of the 1-byte opcode 0xe8, followed by a placeholder for the 32-bit PC relative reference to the target sum. So it's all zeros. I think you can include an add-in by having a value there instead of putting all zeros. The corresponding relocation entry R consists of 4 fields: r.offset, r.symbol, r.type, and r.addend. These fields tell the linker to modify the 32-bit PC relative reference starting at the offset F so that it, EF, yeah, that makes sense, so that it will point to the sum routine at runtime. Now suppose that the linker has determined that adder of S equals adder text, which is 440. Let's see here. And adder R symbol is equal to adder sum, is equal to 48. Using the algorithm to figure 710, the linker first computes the runtime address of the reference and then updates the reference so that it will point to the sum routine at runtime line 8. Okay, in the resulting executable object, the call instruction has the following relocated form. Because it's 5 off from its current location, yeah. At runtime, the call instruction will be located at address so-and-so. When the CPU executes the call instruction, the PC has a value of so-and-so, which is the address of the instruction immediately following the call instruction. To execute the call instruction, the CPU performs the following steps. Push PC onto the stack. Thus, and then 2, PC is equal to PC plus 5. Thus, the next instruction to execute is the first instruction of the sum routine, which of course is what we want. Relocating absolute references. Relocating absolute references is straightforward. For example, in line 4, figure 711, the mov instruction copies the address of array, a 32-bit immediate value, into register EDI. The mov instruction begins at section offset 0x9, and consists of 1 byte opcode BF, and then 4 bytes followed by placeholder with 32-bit absolute reference to array. The corresponding relocation entry R consists of 4 fields. So it says A, which is after BF, which is where the start of the zeros are. The symbol is array. The type is just an absolute 32 and no addend. These fields tell the linker to modify the absolute reference starting at offset 0xa so that it will point to the first byte of array at runtime. Now suppose that the linker has determined that adder of array symbol is equal to adder array, which is equal to that. The linker updates the original reference in line 13 of their algorithm. Resulting in executable object file, the reference has the following relocated form. Putting it all together, figure 712 shows the relocated text and data sections in the final executable object file. At load time, the loader can copy the bytes from these sections directly into memory and execute the instructions without any further modifications. Because 601018 is the array, yep. And plus 5 would be, if you're here, you want to go 1, 2, 3, 4, 5. I don't really get why the addend, I need to fully grok why we need to have an addend of -4 on the relative indexing. Something about how the PC go back to the algorithm. So we have, normally we just take the adder of the symbol and you add the addend. And that's the thing that we're going to point to. But here we have to take the adder of the symbol, add the addend, and remove the reference adder. The reference adder is the adder of the symbol, or adder of S, which is adder of the section plus the offset. So we're subtracting that off. So we have the adder of the symbol where we want to go to, which is there. We have the adder of the section start plus the offset, which would be there. We subtract the 2, and that gives us distance relative. Okay, and then we have to subtract 4. I get it. Because 4 is the width of the data that we're filling in. And will be after that data. Once we run the instructions, the program counter will be after that data. That makes sense. Okay. All right, practice problem 7.4. Let's load up our problems. Hey. Let's Let's go back here. 7.4. Okay. The problem concerns the relocated program in figure 712A, which is up here, the text section. Says, what is the hex address? What is the hex address of the relocated reference to sum in line 5? Oh, these are going to be easy. Just to make sure that you're paying attention. It's not really challenging at all. What is the hex address of the relocated reference to sum in line 5? Would be 0x 4004E8. Oops, too many x's. And then what is the hex value of the what is the hex value of the relocated reference to sum? That would be 5. Let me just say 5. Okay, let's check at the back of the book, make sure we understood the nature of the problem here. 7.4. 4004D. I did not get that right, but I did get the second one right. So let's rewrite the question. What is the hex address of the relocated reference to sum in line 5? Oh, the actual address of the reference. Okay, that makes sense. It says 404DF. Okay. I thought they meant what did it resolve the sum address to. Okay, this problem concerns a disassembly listed in so-and-so. Our purpose here is to give you some practice reading disassembly listings and to check your understanding of PC relative addressing. The hex address of the relocated reference in line 5 is that the hex value of the relocated reference is 5. Remember that disassembly listing shows the value in the reference in little endian byte order. No shit. Alright, and then we'll do 7.5 as well. So this is consider the call to function swap in object m.o. We don't have that, but we do have this here. So we have a call to swap, and it has no address so far. It looks like a PC relative call. So with the following relocation entry, so we say A, yep, that's correct. Symbol is swap. It's PC relative and -4 because that's the size of the byte sequence. Now suppose that the linker relocates text in m.o to address 4004D0 and swap address to 4004E8. Then what is the value of the relocated reference to swap in the call queue instruction? Okay, well that's going to be 0x4004D0. So that's the new base of text. 0x9 would be old offset of, let's say OG offset of call instruction, and then we say A, OG offset of swap ref inside instruction, and then it's going to relocate that, so we have to add A basically onto this. So it'll be 0x4004DA would be the new offset onto text. That's text. Doesn't matter where swap wound up. then what is the value of the relocated reference to swap? Oh, that would be the so this would be the new ref offset of swap ref, but actually that's not what they're asking for. They're asking the value. So 0x4004E8 is going to be the new offset of swap itself, new location of swap. Then we have to get it's going to be this minus this plus or minus 4, this minus that minus 4. So that minus that minus 4. And if we just dump that into Python real quick here, should be able to compute that as 10. If we get the hex of that, it should be A. Yeah. So value of PC ref is going to be 0xa. Let's check our answer here. Yep. The problem tests your understanding of how the linker relocates PC relative references. You were given that so-and-so and so-so using the algorithm figure 710. The linker first computes the runtime address of the reference, then updates the reference. Thus, in the resulting object file, the PC relative reference to swap has a value of 0xa. Booyah. Cool. Alright, kill that. On to the next section, executable object files. And we're done with all of our problems for the chapter, which is nice. Which means we're coming to an end to the chapter. Executable object files. We have seen how linker merges multiple object files in a single executable object file. Our example C program, which began life as a collection of ASCII text files, has been transformed into a single binary file that contains all of the information needed to load the program into memory and run it. Figure 713 summarizes the kinds of information in a typical ELF executable file. So we got our header, our segment header table, or also known as the program header table, which is runtime segments. We got sections and then a section header table. So the segment header table maps contiguous file sections to runtime memory segments. This is all read-only memory segment, code segment. Then we have read-write memory segment, which is data segment. And then symbol table and debugging info are not loaded into memory. And section header table just describes the sections. Okay. The format of an executable object file is similar to that of a relocatable object file. The ELF header describes the overall format of the file. It also includes the program's entry point, which is the address of the first instruction to execute when the program runs. The text, RO data, and data sections are similar to those in a relocatable object file, except that these sections have been relocated to their eventual runtime memory addresses. The init section defines a small function called _init that will be called by the program's initialization code. Since the executable is fully linked, relocated, it needs no .rel sections. ELF executables are designed to be easy to load into memory with contiguous chunks of the executable file mapped to contiguous memory segments. This mapping is described by the program header table. Figure 714 shows part of the program header table for our example executive program as displayed by ObjJump. Let's take a look at that. So we got read-only code segments and read-write data segments. So this seems to be a read execute. So this is probably your text. And then read write is our data, yeah. So it says load offset is 0. The virtual address to load it into will be at 4,000 or 400,000. Physical address Not sure why we need a physical address. Align 2 to the power 21. Okay. That's like, what? Isn't that like several megs? Yeah, Python. Because 2 to the power of 20 would be 1 meg. So 21 would be 2 megs. Like, why does it need a line to 2 megs? I guess p-adder would be the, no. I guess can't really explain any of that. File Z, I don't quite understand that. Or memz. Flags, I understand. Program header table for the example executive program offset in the object file. V-adder, p-adder, memory address. But like, why does it have to be the same? Or does it have to be the same, or couldn't they be different? Why have 2 values if they can't be different? If they are different, what do they mean? What are their semantics? Alignment requirement, file Z, segment size in object file. Memz, segment size in memory. Okay. So it has the same size. And then flags, runtime permissions. Let's go here. From the program header table, we see that 2 memory segments will be initialized with the contents of the executable object file. Lines 1 and 2 tell us that the first segment is a code segment, has read to execute permissions, start at memory address 400,000, has a total size in memory of 69C bytes, and is initialized with the first 69C bytes of the executable object file, which includes the elf header, the program header table, and the init text and RO data sections. Line 3 and 4 tell, does it contain, okay. I guess, yeah, it starts with offset 0. So the whole fucking thing gets loaded in. Alright, lines 3 and 4 tells us that the second segment, the data segment, has read-write permissions and starts at memory address 600,000 DF8 and has a total memory size of 230 in hex bytes, and is initialized with the 0x228 bytes in the data section starting at offset 0xDF8 in the object file. The remaining 8 bytes in the segment correspond to BSS data that will be initialized to 0 at runtime. For any segment S, the linker must choose a starting address, v-adder, such that v-adder mod align is equal to offset mod align. Okay. Let's fully correct that. So v-adder is just a location in the actual memory of the process. Mod alignment. Okay, so it doesn't have to be aligned to that boundary. It just, that's the thing that you do the modulus on to make sure that it fits in that alignment block. So it says where off is the offset of segment's first section of the object file, and align is the alignment specified in the program header. Okay, that makes sense. That's why it goes from 400,000 in hex to 600,000 hex. Okay. This alignment requirement is an optimization that enables segments in the object file to be transferred efficiently to memory when the program executes. The reason is somewhat subtle, and it's due to the way that virtual memory is organized as large contiguous powers of 2 chunks of bytes. You will learn about virtual memory in Chapter 9. Loading executable object files. loading executable object files. To run executable object, the file prog, we type its name into Linux shell command line. Since prog does not correspond to a built-in shell command, shell assumes that prog is an executable object file, which it runs for us by invoking some memory. Actually, when you do // it has to be on the files. It doesn't use built-ins for that. Which it runs for us by invoking some memory resident operating system code known as the loader. Any Linux program can invoke the loader by calling execve function, syscall, which we will describe in detail in section 846. The loader copies the code and data in the executable object file from disk into memory, and then runs the program by jumping to its first instruction or entry point. The process of copying the program into memory and then running it is known as loading. Every running Linux program has a runtime memory image. Let me highlight this. Every running Linux program has a runtime memory image similar to the one in figure 715. Let's take a look at it. So it's what you expect at 400,000 read-only code segment, read-write segment, runtime heap, memory mapped regions for shared libraries. There's also the memmap stuff, the manual memory mapping, user stack, kernel memory. Cool. On Linux x86-64 systems, the code segment starts at address 400,000 followed by the data segment. The runtime heap follows the data segment and grows upwards via calls to the malloc library. We describe malloc and the heap in detail in section 9.9. This is followed by a region that is reserved for shared modules. The user stack starts below the largest legal user address to the power 48 minus 1 and goes downward towards smaller memory addresses. The region above the stack, starting at address 2 to the power 48, is reserved for code and data in the kernel, which is the memory resident part of the operating system. For simplicity, we've drawn the heap data and code segments as abutting each other, and we placed the top of the stack at the largest legal user address. In practice, there's a gap between the code and data segments due to alignment requirements on the data segment. We saw that just a moment ago. Also, the linker uses address space layout randomization, ASLR, when it assigns runtime address to the stack, shared library, and heap segments. Even though the location of these regions change each time the program is run, their relative positions are the same. When the loader runs, it creates a memory image similar to the one shown in figure 715. Guided by the program header table, it copies chunks of the executable object file into code and data segments. Next, the loader jumps to, actually, let me ask AI a quick question. What segments does ASLR alter? What segment addresses? You know what I mean. So we got the stack base. The top of the stack is randomized each run. This affects return addresses, local variables, etc. Heap. The heap break mmap allocations starts at a randomized base. Makes heap-based exploits less predictable. Shared libraries, SOs, dynamically loaded libraries like libc are mapped at random addresses. It's one of the most important protections. Memory mapped regions. Anything loaded via mmap, files in anonymous memory, gets randomized placement. I don't think that's part of ASLR, that I think it's just how mmap functions, and you can give mmap specific addresses you want to map to. And the kernel, I think it's like a hint of the kernel to put it there. Executable pi only. So the executable base, portable, position independent executable. If the binary is compiled as position independent executable, its text data segments are loaded at a random base. If not position independent, the executable is loaded at a fixed address, just like something like 400,000. Okay. Next, the loader jumps to the program's entry point, which is always the address of the underscore start function. This function is defined as the system object in the system object file crt1.o, and is the same for all C programs. The start function calls the system startup function, which is libc start main, which is defined in libc.so. It initializes the execution environment, calls the user level main function, handles its return value, and if necessary, returns control of the kernel. Dynamic linking with shared libraries. The static libraries that we've studied in section 7.6.2 address many of the issues associated with making large collections of related functions available. Oh, fuck, man. I'm so tired. All right. Let me start this over again. Dynamically with shared libraries. The static libraries that we have studied in section 7.6.2 address many of the issues associated with making large collections of related functions available to application programs. However, static libraries still have some significant disadvantages. Static libraries, like all software, need to be maintained and updated periodically. If application programmers want to use the most recent versions of a library, they must somehow become aware that the library has changed and then explicitly relink their programs against the updated library. Another issue is that almost every C program uses standard I/O functions such as printf and scanf at runtime. The code for these functions is duplicated in text segments of each running process. On a typical system that running hundreds of processes can be a significant waste of scarce memory system resources. An interesting property of memory is that it is always a scarce resource regardless of how much there is in a system. Disk space and kitchen trash cans share the same property. Shared libraries. Before we move on there, let's read our aside. Our description of loading is conceptually correct, but intentionally not entirely accurate. To understand how loading really works, you must understand the concepts of process, virtual memory, and memory mapping, which we haven't discussed yet. As we encounter these concepts later in chapter 8 and 9, we will revisit loading and gradually reveal the mystery to you. For the impatient reader, here's a preview of how loading really works. Each program in a Linux system runs in the context of a process with its own virtual address space. When the shell program runs, the parent shell process forks a child process that is a duplicate of the parent. The child process invokes a loader via execve system call. The loader deletes the child's existing virtual memory segments and creates a new set of code, data, heap, and stack segments. The new stacks and heap segments are initialized to 0. The new code and date segments are initialized to the contents of the executable file by mapping pages in the virtual address space to page-sized chunks of the executable file. Finally, the loader jumps to the start address, which eventually calls the application's main routine. Aside from some header information, there is no copying of data from disk to memory during loading. The copying is deferred until the CPU references a mapped virtual page, at which point the operating system automatically transfers the page from disk to memory using its paging mechanism. Shared libraries are modern innovations that address the disadvantages of static libraries. A shared library is an object module that at either runtime or load time can be loaded into an arbitrary memory address and linked with a program in memory. This process is known as dynamic linking and is performed by a program called a dynamic linker. Shared libraries are also referred to as shared objects. And on Linux systems, they are indicated by .so suffix. Microsoft operating systems make heavy use of shared libraries, which they refer to as DLLs, dynamic link libraries. Shared libraries are shared in two different ways. First, they are given files. In any given file system, there's exactly one .so for a particular library. The code and data in this .so file are shared by all executable object files that reference the library, as opposed to the contents of the static libraries, which are copied and embedded in the executables that reference them. Secondly, a single copy of the text section of a shared library in memory can be shared by different running processes. We will explore this in more detail when we study virtual memory in Chapter 9. Figure 7.16 summarizes the dynamic linking process of the example program in Figure 7.7. To build a shared library libvector.so of our example vector routines, in Figure 7.6, we invoke the compiler driver with some special directives to the compiler and linker. So we say, hey, I want to build a shared position-independent code, output to libvector.so, and here are my C files. The -fpic flag directs the compiler to generate position-independent code. More on this in the next section. Shared flag directs the linker to create a shared object file. Once we have created the library, we would then link it in our example program Figure 7.7. Let's look at the diagram. So, yeah, totally makes sense. Not unfamiliar with this. So you link against libvector.so, or you can say -l vector. This creates an executable object file, prog21, in a form that can be linked with libvector.so at runtime. The basic idea is to do some of the linking statically when the executable file is created. And then complete the linking process dynamically when the program is loaded. You know what would be really cool is like, if you, I know there's like, what's the name of it? Filcy. But what would be cool is like, I guess I go around the moon. What would be cool is if you could use all of the traditional C compiler infrastructure, but have a memory safe kind of like mode to C, where it was more strict with undefined behavior, where bounds, like basically take the C language and make it memory safe like fill C does. It'd be nice if you could like mix and match like that, where like most of your program is in the memory safe C, which does bounds checking and all that. Or it could even be like a extension on C if necessary. Like it doesn't have to be actual C, but it'd be cool if you could just have like the same language, but either the same language or an evolution of the language that allows it to be, compiled into an efficient memory safe program. And that would just like do away with all the need for like Rust and all these other like memory safe languages. I mean, not entirely. Like obviously there's reasons why those languages exist beyond just memory safety, but a lot of people, I feel like, move from like C to Rust just for the memory. I mean, look at the Linux kernel. People want memory safety. They don't have to want to have to deal with all this memory bullshit. That would be really cool, because then you could just like use all of the compiler infrastructure that we have, all the binary formats that we have, all the tooling that we have, and everything would follow the C ABI, and we wouldn't have to like have all these different like incompatible languages that all talk to each other over the C ABI. And I'm not a big fan of runtimes either. Like when Go compiles your code and you look at it and it's like, it puts all these like runtime calls in it everywhere. It's like, I don't want that stuff in there. I know it helps you. I know it provides functionality for like the average programmer. Who doesn't want to have to deal with all this like evented IO and async IO and networking sockets and stuff like that. They just want a high level interface that just works. They don't have to deal with threads. And whether the threads are blocking or not, like. But yeah, that would be pretty cool if you could have something like that. Because C is a great language, it's just not very safe. So if you could eliminate that, if you do what the Phil C guy was saying, but like do it in a way that's like really performant and is CABI compatible and allows for like projects to have it enabled for some compilation units and others have it disabled, I think that would be like a really awesome solution to that problem. I'm not capable of doing that. I don't even know if it's possible, but the Phil C guy seems to be like making a lot of progress. Maybe he'll eventually get there. Okay, the base idea is to do some of the static linking when the executable file is created, and then complete the linking process dynamically when the program is loaded. It is important to realize that none of the code or data sections from libvector.so are actually copied in the executive program prog21 at this point. Instead, the linker copies some relocation symbol table information that will allow references to code and data in libvector.so to be resolved at load time. When the loader loads and runs the executable prog21, it loads the partially linked executable prog21 using the techniques discussed in section 7.9. Next, it notices that prog21 keeps a interp section which contains the path name of the dynamic linker, which is itself a shared object. Instead of passing control to the application, as it would normally do, the loader loads and runs the dynamic linker. The dynamic linker then finishes the linking tasks by performing the following relocations. So relocating the text of the data of libc.so into some memory segment, relocating text and data of libvector.so to some other memory segment, relocating any references in prog21 to symbols defined by libc and libvector.so. Finally, the dynamic linker passes control to the application. From this point on, the locations of the shared libraries are fixed and do not change during execution of the program. Loading and linking shared libraries from applications. Up to this point, we have discussed a scenario in which the dynamic linker loads and links shared libraries when the application is loaded. Just before it executes, however, it is also possible for an application to request the dynamic linker to load and link arbitrary shared libraries while the application is running, without having to link to the applications against those libraries at compile time. Dynamic linking is a powerful and useful technique. Here are some examples of real world. Distributing software. Developers of Microsoft Windows applications frequently use shared libraries to distribute software updates. They generate a new copy of a shared library, which users can then download and use as a replacement for the current version. The next time they run their application, it will automatically link and load the new shared library. Built-in high-performance web servers. Many web servers generate dynamic content, such as personalized web pages, account balances, and banner ads. Early web servers generated dynamic content using fork and exec to create child processes to run CGI programs in the context of the child. However, modern high-performance web servers can generate dynamic content using a more efficient, sophisticated approach based on dynamic linking. The idea is to package each function that generates dynamic content in a shared library. I've never seen this in production. When the request arrives from a web browser, the server dynamically loads and links the appropriate function and then calls it directly, as opposed to using fork and exec to run the function in the context of a child process. The function remains cached on the server's address space, so subsequent requests can be handled at the cost of simple function call. This can have a significant impact on the throughput of a busy site. Further, existing functions can be updated and new functions can be added at runtime without stopping the server. Linux systems provide a simple interface to the dynamic linker that allows application programs to load and link shared libraries at runtime. Just DL open, very familiar with that. DL sim. DL open function loads and links the shared library file name. The external symbols in file name are resolved using the libraries previously opened with the RTLD global flag. If the current executable was compiled with the R dynamic flag, then its global symbols are also available for simple resolution. The flag argument must include either RTLD now, which tells the linker to resolve references to external symbols immediately, or RTLD lazy, which instructs the linker to defer simple resolution until the code for the library is executed. Either of these values can be ORed with the RTD global flag. Okay. DLSim handle character string. The DLSim function takes a handle to a previously opened shared library and a symbol name and returns the address of the symbol if it exists or null otherwise. DLClose. DLClose function unloads the shared library if no other shared libraries are still using it. DLError. DLError function returns a string describing the most recent error that occurred as a result of calling DLOpen, DLSim, or DLClose, or null if no other error occurred. Figure 717 shows how we would use this interface to dynamically link our libvector.so shared library at runtime and then invoke its addvec routine. To compile the program, we would invoke GCC the following way. Okay, this is our DLL.c. Okay, so we have a section on position independent code, library into positioning, and I think that's it for the chapter. And a summary, yeah. Or I guess there's a small section for tools and for manipulating object files. which are all tools we're familiar with. So we will definitely finish this chapter today. We're about to finish in the next hour or so. I guess I could get started on the lab. The cache lab, I think we had to create a cache simulator. I was kind of avoiding that because I didn't really want to emulate the caches. Like, seemed kind of boring. But maybe that's what I need to do, is that lab. What I'll do is I'll take a break after this chapter, like a quick 5-10 minute break, just to mentally kind of like reset, and then come back to the lab with kind of a perspective of curiosity. That's what I'm going to try to approach this with, because right now my mindset is like, I don't want to simulate a cache like a hardware CPU cache. Like I just don't want to do it. Like, the CPU has a great implementation. Like, why would I want to even simulate it? But I'm sure it's a worthwhile exercise. I've gotten a lot of benefit out of most of the labs so far. So yeah, I'll take a break. I'll come back to it from the perspective of curiosity and the perspective of I don't have to do shit on it, because I can take my time. Like, I don't have to like feel rushed into getting it done before dinner or whatever. I could take my time into the next couple streams working on it. I can read other things. I'll take the perspective of like, let's do 5 minutes of work, and then we can take a break and do anything else. We can read other books. We can do Brilliant. We can watch lectures. We can read blog posts. We can watch talks. You know, we have a whole repo of things that we want to accomplish, that we've documented things that we want to accomplish. We could even work on side projects like the ePOL file server or anything. So keeping it like my options open like that kind of reduces the feeling that I have of like not wanting to do it, hopefully. And if not, I'll do something else. It's fine. Okay, so let's go back over here. This is the code for the program that we're creating here. Which I've written code like this before in the past, where you call deal open, and then you call deal sim, and then you call add vec, and then you call deal close. Yeah, nothing crazy there. Aside, shared libraries and the Java native interface. We're almost done with this freaking book, man. We finished that much of the book, and there's only that much left. All right, shared libraries in the Java native interface. Java defines a standard calling convention called the Java native interface that allows native C and C++ functions to be called from Java programs. The basic idea of JNI is to compile the native C function, say foo, into a shared library, say foo.so. When a running Java program attempts to invoke function foo, The Java interpreter uses the deal open interface or something like it to dynamically link and load foo.so and then call foo. Position independent code, PIC. This is, I know the pieces of position independent code, like the global offset table and the procedure link table, I think it's called. The PLT is like actual code stubs that you call into that then look at the global offset table, and if the offset hasn't been resolved, if like the relocation hasn't been patched in the offset table, then the linker is invoked, go out and like load the shared object, which then does the relocations, patches the global offset table, returns back to the PLT, and then allows the PLT to call indirectly through the global offset table. So I understand the machinery of how it works, but I haven't really spent any time actually reading about how it works. I've just kind of like picked this up from like chats with AI and my own investigations. So excited to read this section. Position independent code. A key purpose of shared libraries is to allow multiple running processes to share the same library code in memory and thus save precious memory resources. So how can multiple processes share a single copy of a program? One approach would be to assign a priori a dedicated chunk of the address space to each shared library, and then require the loader to always load the shared library at that address. While straightforward, this approach creates some serious problems. It would be an inefficient use of the address space because portions of the space would be allocated even if the process didn't use the library. It would also be difficult to manage. We would have to ensure that none of the chunks overlapped. Each time a library is modified, we would have to make sure that it still fit in the assigned chunk. If not, then we would have to find a new chunk. And if we created a new library, we would have to find room for it. Over time, given the hundreds of libraries and versions of libraries on the system, it would be difficult to keep the address space from fragmenting into lots of small, unused, but unusable holes. Even worse, the assignment of libraries to memory would be different for each system, thus creating even more management headaches. To avoid these problems, modern systems compile the code to segments of shared modules so that they can be loaded anywhere in memory without having to be modified by the linker. With this approach, a single copy of a shared module's code segment can be shared by an unlimited number of processes. Of course, each process will still get its own copy of the read-write data segment. Code that can be loaded without needing any relocations is known as position-independent code. Users direct GNU compilation systems to generate position-independent code with the FPIC option in GCC. Shared libraries must always be compiled with this option. On x86-64 systems, references to symbols in the same executable object module require no special treatment to be PIC. These references can be compiled using PC relative addressing and relocated by the static linker when it builds the object file. However, references to external procedures and global variables that are defined by shared modules requires some special techniques, which we describe next. PIC data references. Compilers generate PIC references to global variables by exploiting the following interesting fact. No matter where we load an object module, including shared object modules in memory, the data segment is always the same distance from the code segment. Thus, the distance between any instruction in the code segment and any variable in the data segment is a runtime constant, independent of the absolute memory locations of the code and data segments. Compilers that want to generate PIC references to global variables exploit this fact by creating a table called the global offset table at the beginning of the data segment. The global offset table contains an 8-byte entry for each global data object, procedure, or global variable that is referenced by the object module. The compiler also generates a relocation record for each entry in a GOT. At load time, the dynamic linker relocates. Hey, see, as I said, it does a relocation. You're over here saying that the relocations aren't required. Generates a relocation record for at load time, the dynamic linker relocates each GOT entry so that it contains the absolute address of the object. Each object module that references global objects has its own GOT. Figure 718 shows the GOT from our example libvector.so. Shared module. Using the GOT to reference a global variable. So we got our global offset segment at the beginning of the data segment, global offset table at the beginning of the data segment, and the third element of that array is a fixed distance from add L. So RAX is equal to GOT3 is equal to add count. So this says take the instruction pointer, which has been modified already to point to add L, add this offset, and that's the position of the, and dereference that value. And store that in RAX. No, that's the global offset location. And then add L says take one and store that, the dereferencing of that location. Okay. Figure 718 shows that GOT from our example libvector as a shared module. The add vector routine loads the address of the global variable add count indirectly via GOT3 and then increments add count in memory. The key idea here is that the offset in the PC relative reference to GOT3 is a runtime constant. Since add count is defined by the libvector.so module, the compiler could have exploited the constant distance between the code and data segments by generating a direct PC relative reference to add count and adding a relocation for the linker to resolve when it builds a shared module. However, if add count were defined by another shared module, then the indirect access through the GOT would be necessary. In this case, the compiler has chosen to use the most general solution for GOT for all references. Yeah, I was going to say, if it's in the data segment, you can just boop, and you know the offset, and just point right to it instead of going through an indirection. PIC function calls. Suppose that a program calls a function that is defined by a shared library. The compiler has no way of predicting at the runtime address of the function, since the shared module that defines it could be loaded anywhere at runtime. The normal approach would be to generate a relocation record for the reference, which a dynamic linker could then resolve when the program was loaded. However, this approach would not be position independent since it would require the linker to modify the code segment of the calling module. GNU compilation systems solve this problem using an interesting technique called lazy binding that defers the binding of each procedure address until the first time the procedure is called. The motivation for lazy binding is that a typical application program will call only a handful of the hundreds or thousands of functions exported by a shared library such as libc.so. By deferring the resolution of a function's address until it's actually called, the dynamic linker can avoid hundreds or thousands of unnecessary relocations at load time. There is a non-trivial runtime overhead the first time the function is called, but each call thereafter costs only a single instruction and a memory reference for the indirection. Lazy binding is implemented with a compact yet somewhat complex interaction between the two data structures, the GOT and the procedure link table. If the object module calls any function that are defined in shared libraries, then it has its own GOT and PLT. The GOT is part of the data segment, the PLT is part of the code segment. Figure 719 shows how the PLT and GOT work together to resolve the address of a function at runtime. So we have a data segment with our GOT. And then we have a code segment with our PLT, which says push quad word got1 jump to got2. Using the PLT and GOT to call external functions, the dynamic linker resolves the address of advec the first time it's called. So first, let's examine the contents of each of these tables. The procedure link table, the PLT is an array of 16-byte code entries. Okay. So it's got 2 pointers. PLT 0 is a special entry that jumps into the dynamic linker. Each shared library function called by the executable has its own PLT entry. Each of these entries is responsible for invoking a special function PLT1, not shown here, invokes the system startup function, libc start main, which initializes the execution environment, calls the main function, and handles the return value. Entries starting at PLT2 invoke functions called by the user code. In our example, PLT2 invokes advec, and PLT3, not shown, invokes printf. Global offset table. As you'll see in the GOT is an array of 8-byte address entries. When used in conjunction with the PLT, GOT0 and GOT1 contain information that the dynamic linker uses when it resolves function addresses. GOT2 is an entry point for the dynamic linker in the ld-linux.so module. Each of the remaining entries corresponds to a called function whose address needs to be resolved at runtime. Each has a matching PLT entry. For example, GOT4 and PLT2 correspond to advec. Initially, each GOT entry points to the second instruction in the corresponding PLT entry. Okay. Figure 719 shows how the GOT and PLT work together to lazily resolve the runtime address of the function advec the first time it is called. Step 1. So we call into our PLT. Instead of directly calling advec, the program calls into PLT2, which is the PLT entry for advec. So that says jump quad word to the dereference of GOT4. But GOT4 hasn't been resolved yet, right? The first PLT instruction does an indirect jump through GOT4, which each GOT entry initially points to the second instruction of the corresponding PLT entry. Okay, that's a really crazy way of doing it, but it makes sense. The indirect jump simply transfers control back to the next instruction in PLT2. So now we're down at push quad word 1. After pushing an ID for advec on the stack, PLT2 jumps to PLT0. PLT0 pushes an argument for the dynamic linker indirectly through GOT1, and then jumps into the dynamic linker indirectly through GOT2. The dynamic linker uses the 2 stack entries to determine the runtime location of advec, overwrites GOT4 with this address, and passes control to advec. Figure 719b shows the control flow for any subsequent invocations of advec. Control passes to PLT2 as before, and then it just calls through the table because it's been resolved. However, this time the indirect jump through GOT4 transfers control directly to advec. So it's basically the same idea that I had in my head already, except this actually has some of the disassembly, and I wasn't aware of the actual instructions used and how it does the indirect call initially no matter what. And it's just initially put in the next instruction. So a little bit more detail. I appreciate that though. Library interpositioning. Linux linkers support a powerful technique called library interpositioning that allows you to intercept calls to shared library functions and execute your own code instead. Using interpositioning, you could trace the number of times a particular library function is called, validate and trace its input and output values, or even replace it with a completely different implementation. So I was familiar with the LD preload, but they go through other options with static linking interpositioning and C preprocessor interpositioning. Okay. I really value that I've gone through this chapter because I'm getting a lot better understanding for like how C works under the hood and all these libraries as well. Like when you're writing C, like all you're doing is producing, like the file that you're currently authoring is producing a compilation target, or sorry, a compilation unit, or they call it a module in this book. I don't know what the correct terminology is, but basically a .o file. That's what you're creating. And it's a relocatable .o file that you then combine with other .o files to generate an actual executable binary. And then that binary can also be optionally dynamically linking against other libraries that get resolved either at load time or at runtime. And some of the questions I had around how symbols are resolved in C are now kind of answered because I know more about the linker, and the linker does that symbol resolution. So when you're creating your object file, you can specify which symbols are available for other object files to use or not. It's kind of like exporting to other packages. But in C, it's like compilation units, and it uses the local and global symbols in the symbol table. And in the actual language of C, that's controlled by whether you have an extern, or where you have a an extern or a static or nothing. So yeah, knowing some of these details of the linker really helps me understand how compilation works in C to produce like the effects that you see. And then header files are just like text files that have forward declarations and struct definitions. for you to be able to reference and then pull in externally. I always had a question though, like when you say like, okay, I'm gonna pound include, say like libzmq, like how does it know to go to like libzmq.so to get those symbols resolved, like for the implementation of those calls? And the answer is the linker, or specifically the dynamic linker. Because when you compile your program, you're gonna say like, I have these dependencies, like this guy. You save which libraries you're linking against as these values here, and then at runtime the dynamic linker goes out and finds those objects. And you can have objects that have conflicting symbols, but that would fail at link time, I think. Like if I'm linking against two different dynamic libraries at link time producing my binary, the linker is going to say, hey, you have two SO libraries that are producing these symbols and they conflict. So it probably uses the same rule with like strong and weak declarations, but like if there's a conflict, it's just going to abort like it does with static linking, because it knows that information at link time. So you'll never get to a situation at runtime where the dynamic linker doesn't, where it's ambiguous to the dynamic linker which library to use for your implementation. What's interesting is like you can use this interpositioning stuff with LD preload to add your own library, which has its own same symbols, and have those replace the ones that I would normally otherwise use. So if I did like a CP, I'm just gonna do a test here. CP of user libc.so.6 to here, and then I say LDD, but I do it with LD preload is equal to $PWD. From LDB. From LD preload cannot be preloaded. Cannot read file data. Maybe I need to specify the full path and say, hey, also libc.so.6. Look at that. I was able to override it with my own version of libc. So it's as simple as that to intercept what it's mapping to, which is crazy because like this thing here is hard coded. Could I override that thing too? What if I did like CP of that to here, and then I did LD, yeah, floating point exception, core dumped. I guess I didn't like that. The dynamic linker I think is a special boy. Alright, let's delete these files because they're in the wrong directory anyways. RM LD Linux and RM libc. Okay. Alright, where do we leave off here? All right, let's start up here. I think we might have been living off of here. Here's a basic idea. Given some target function to be interposed on, you create a wrapper function whose prototype is identical to the target function using some particular interpositioning mechanism. You then trick the system into calling the wrapper function instead of the target function. The wrapper function typically executes its own logic, then calls the target function and passes its return value back to the caller. Interpositioning can occur at compile time, link time, or runtime as the program is being loaded and executed. To explore these different mechanisms, we will use the example program from 720A. As a running example, it calls the malloc and free functions from, what's 720A? Okay. It calls the malloc and free functions from the C standard library. The call to malloc allocates a block of 32 bytes from the heap and returns a pointer to the block. The call to free gives the block back to the heap for use by subsequent calls to malloc. Our goal is to use interpositioning to trace the calls to malloc and free as the program runs. Compile time interpositioning. Figure 720. So let's just look at 720 already. So we just have a malloc, a free, and a return. This actually is not a function call, and the parentheses are not needed. I don't know why they wrote it that way, because return is a statement. All right, and then we got malloc.h file, which just has some pound defines for malloc to be my malloc and define free to be my free, and then it does a for declaration for my malloc and my free, and then wrapper functions in my malloc.c, which are a separate compilation unit, and we say if def compile time. Then we include this stuff. Okay. So let's go back to here. Compile time interpositioning. So 720 shows a C preprocessor, shows how to use a C preprocessor to interpose at compile time. Each wrapper function in my malloc.c calls the target function, prints a trace, and returns the local malloc.h header file. The local malloc.h header file instructs the preprocessor to replace each call to a target function with a call to its wrapper. Here's how to compile time link program. So you say, hey, I'm going to compile with the compile time thing declared or defined. Don't know why you need that. Yeah, and then we just link everything together. The interpositioning happens because of the -i argument. It tells the C preprocessor to look at malloc.h in the current directory before looking in the usual system directories. Oh, okay. I'm gonna highlight that. Notice that the wrappers in mymalloc.c are compiled with the standard malloc.h. header file. Running the program gives the following trace. Link time interpositioning. The Linux static linker supports link time interpositioning with the wrap F flag. This flag tells the linker to resolve references to symbol F as __wrapf, 2 underscores for the prefix, and to resolve symbols to resolve references to symbol real F, 2 underscores as F. Figure 721 shows the wrappers of our example program. Here's how to compile the source files into relocatable object files. Link time, myalloc. Yep. And so that is a different one. which uses the link wrap flag. Linker wrap flag. And here's how to link the object files in executable. So before we were giving this flag to the linker, so we have to do WL. The WL option flag passes option to linker. Each comma in the option is replaced by a space. So we say wrap malloc, and wrap free. Running the program gives the following trace. Runtime interposition. This is the funnest one. LD preload. Compile time interpositioning requires access to program source files. Link time interpositioning requires access to relocatable object files. However, there's a mechanism for interpositioning at runtime that requires access to only the executable object file. This fascinating mechanism is based on the dynamic linker's LD preload environment variable. If LD preload environment variable is set to the list of shared library path names, separated by spaces or colons, then when you load and execute a program, the dynamic linker will search the LD preload libraries first, before any other shared libraries when it resolves undefined references. With this mechanism, you can interpose on any function in a shared library, including libc.so, when you load and execute any executable. Figure 722 allows the wrappers for malloc and free, shows the wrappers for malloc and free. 722. So yeah, you just define malloc and free as you normally would. And it's gonna look up malloc and free at runtime using dlsim, okay, and rtld next. I didn't think of that. Figure 722 shows wrappers for malloc and free, and each wrapper, the call to dlsim returns the pointer to the target libc function. The wrapper then calls the target function, prints a trace, and returns. Here's how to build this shared library that contains the wrapper functions. So you say gcc d runtime shared. D runtime is just because they have 3 modes for the same file. But you have to say shared fpic. So just compile it as normal. And then there's LDL. Let me ask AI about this. What is the LDL library flag used for in GCC? Okay. Yeah, it's called. So it's DL versus LD. This is LD.so, the other one's DL. Okay, cool. Where did I leave off here? Okay, here's how to compile, and I want to do this guy here. It's starting to come together. All this stuff, I feel like it's pieces of the puzzle are falling into place. Here's how to compile the main program. Linux gcc-o enter int c. Here's how to compile the program from the bash shell. Here's how to run the program from the bash shell. If you don't know what the shell you're running, yeah, okay. LD preload, and you just give it my malloc.so, and you call it like that, and then you get the interposition on the, I would call it intercepting the library functions. And here's how to run it from CSH TSH shells. Okay, well I don't use those shells. Notice that you can use LD preload to interpose on the library calls of any executable program. Yep. That's the goal. So if you wanted to, here. So using LD preload, I can intercept calls to arbitrary library code that is resolved, that is dynamically linked. How would I go about intercepting code in functions in the .text section of a Linux binary? So uprobes and BPF maybe, or you could probably use ptrace or a debugger that uses ptrace for you. It's a fucking bird that just flew up above my window. Scared the shit out of me. It's like a raven. Frida, that's a good one. I use P-Trace, I believe. I want to do more learning about Frida. Jump over to learn log. Docs. Let's open up this. Okay. Wow, this linker section just went by really fast, especially after I did my cardio. I'm like, I want to learn more. I started off the day just like not really wanting, like eager to learn, and at this point in the day, my brain's just like, this stuff is so cool. I want to learn more. And we're at the end of the chapter here, so I might pick up the Learning Linux Binary Analysis book after this. Yeah, got to chapter 8. Cool. Let's finish this up. Tools for manipulating object files. There are a number of tools available in Linux systems to help you understand and manipulate object files. In particular, GNU built-in utils package is especially helpful and runs on every Linux platform. AR creates static libraries and inserts, deletes, lists, and extracts members. Strings lists all the printable strings contained in an object file. Strip deletes symbol table information of an object file. NM lists the symbols defined in a symbol table of an object file. I haven't really ran that very many times. NM build main. Okay, what does NM stand for? What does NM, the command that prints the symbol table, stand for? Nameless? That's stupid. I mean, I usually use objdump or readelf for the symbol table anyways, but I wanted to try to see if I could find a place in my brain to insert nm, since I don't use it that often. It is a very quick way to just see where the offsets are for the symbols, what type of symbols they are. But there's other symbol data that they're not including there. Okay, so nm size, lists the names and size of sections of an object file. What? M.O? Okay. I've never used size before either. Readelf, I've used that plenty of times. Display the complete structure of an object file, including all of the information coded in the elf headers, subsumes the functionality of size and nm, which is why I haven't really used those. Objdump, the mother of all binary tools, can display all of the information in an object file. Its most useful function is disassembling the binary instructions in the text section. Linux systems also provide the LDD program for manipulating shared libraries, lists the shared libraries that executable needs at runtime. Summary. Linking can be performed at compile time by static linkers and at load time and runtime by dynamic linkers. Linkers manipulate binary files called object files, which come in three different forms: relocatable, executable, and shared. Relocatable object files are combined by static linkers into executable object file that can be loaded into memory and executed. Shared object files, shared libraries, are linked and loaded by dynamic linkers at runtime, either implicitly when calling a program is loaded or begins executing, or on demand when the program calls functions from the OpenDL library. Sorry, DL Open Library. The two main tasks of linkers are symbol resolution, where each global symbol of an object file is bound to a unique definition, and relocation, where the ultimate memory address for each symbol is determined and where references to those objects are modified. Static linkers are invoked by compiler drivers such as GCC. They combine multiple relocatable object files into a single executable object file. Multiple object files can define the same symbol, and the rules that linkers use for silently resolving these multiple definitions can introduce subtle bugs in the user programs. Multiple object files can be concatenated into a single static library. Linkers use libraries to resolve symbol references and other object modules. The left to right sequential scan that many linkers use to resolve symbol references, another source of confusing link-time errors. Loaders map the contents of executable files into memory and run the program. Linkers can also produce partially linked executable object files with unresolved references to the routines. Sorry, let me read this up. My mind was wandering. Loaders map the contents of executable files into memory and run the program. Linkers can also produce partially linked executable object files with unresolved references to the routines and data defined in the shared library. At load time, the loader maps the partially linked executable into memory and then calls a dynamic linker, which completes the linking task by loading the shared library and relocating the references in the program. Shared libraries that are compiled as position-independent code can be loaded anywhere and shared at runtime by multiple processes. Applications can also use a dynamic linker at runtime in order to load, link, and access the functions and data in shared libraries. My question is, like, how does the, like, say your shared object calls another external function in another shared object. How does it know where the PLT exists? Like where the little trampoline PLT thing exists. Let me see if AI can help me understand that. So say I have a shared library that I load into my program, and there is a function in there that I call from my main program. And it has, let's call the if my func calls another function in another shared library, how does it know where the PLT resides for the program, and B, what entry in the PLT maps to the function it needs? Okay, so it uses its own PLT and got, okay. Okay. I mean, the summary was all I needed there to know what I needed to know. Okay, so shared libraries are compiled as position-independent code and can be loaded anywhere in the and shared at runtime by multiple processes. Applications can also use the dynamic linker at runtime in order to load, link, and access the functions and data in shared libraries. Biographic notes. Linking is poorly documented in computer systems literature since it lies at an intersection of compilers, computer architecture, and operating systems. Linking requires an understanding of code generation, machine language programming, program instantiation, and virtual memory. It does not fit neatly into any of the usual computer system specialties and thus is not well covered by the classic text in this area. However, Levine monograph provides a good general reference on the subject. The original IA32 specification for ELF and dwarf are described in 54. The x86-64 extension to the ELF file format are described in 36. The x86-64 application binary interface describes the conventions for compiling, linking, and running x86-64 programs, including the rules for relocation and position independent code. Okay. I feel like I learned a lot from this chapter. I do not want to do any of the homework problems, even though there's not that many. Cool. It's 308. Let's see. I pulled out my phone and totally forgot what I was trying to do because I got so many messages today. We're talking about linkers and shared libraries. Oh, I was gonna take a photo for my iPod. That's all right. Boop. Exceptional control flow. So what do you want to do? Do you want to dive into exceptional control flow text? Do we want to watch a lecture? Do we want to do the lab? We should probably do the lab. I said that I was going to take a break and then come back and do the lab earlier. So this is what I like to see in books. I don't know if you can see that. I have my head. The crescent shape on the binding. That comes from using it. So many books you see on people's shelves, the bindings are pristine. They've never been cracked open. So when I get to the point in reading a book like this one, where it's very visibly used by the binding, the cracks in the binding, I feel a certain amount of pride. I mean, look at how much I've read. Just the amount of pages that are left in the book versus the amount that I've read. We're at 755 out of about 1,100-ish. I mean, a lot of that's like index and other stuff. Could you imagine writing this book? That would be quite the endeavor. That would be quite the endeavor to write all this and formulate all the problems and even put together a course. And I mean, it is a project that takes a village, like all the TAs and editors and all the people that, I mean, graphic designers, publishers, distributors. Like, it is a huge, multifaceted endeavor to produce a artifact like this book. But the amount of labor that these authors went through to produce this, it is quite a significant amount of their life, really. This book is stored life force. Like these authors, Randall E. Bryant and David R. O'Halloran, have, you know, spent their life learning about computer systems, and they distilled that down into course material and a textbook, and this is like their stored life essence, and it's awesome. It's quite incredible the amount of effort that they put into here. I've never participated in a project as grand as this, like creating a artifact like this. I feel like we should have more reverence for academics and people who produce stuff like this, especially stuff that's accessible and approachable. Some people, some professors, some academics produce textbooks that are just brutal. They're not approachable, but this one is very approachable. All right, so I'm putting the textbook up, and I was going to take a break and then come back and we will work on the labs. So let me actually, before I do that, Vim README, we can go up here and we could go down and we can mark off all of the linking stuff. Oops. I didn't really use this time. Getting through the memory stuff was a lot more difficult than the linking stuff. I think it's because I was just like, well, I think the linking was a little bit more reading and less problems, and was more approachable from the position I'm currently at. I could easily move in that direction. It was slightly challenging, not super challenging. I would say it's slightly challenging. I learned a lot. It was completely in my wheelhouse, in my comfort zone. Wasn't too far beyond my area of expertise. All right, so let's pop over to the contents and we'll copy over chapter 8 now. This one I'm not too excited about, not gonna lie, because really virtual memory is the only section I really feel I'm going to get a lot of value out of in the remainder of the text here. Okay, so we have 8 sections, and you know what I'm going to do? I'm going to try to do a percent. I'm going to do a selection, and I'm going to do a colon %s. Or did I just say colon s? I think I say %s. And then I say search for a space and then a digit plus. I have to escape the plus, and then I go to the end of the line and replace that with nothing. I need to do that again. I need to do it. Can I do it like this? How do I think it's a B? Invalid trailing characters. What if I did it like this and I said, hey, just delete this shit? That looks like it works. Okay. I think I probably need to come back here and say part 1, like I, not 1. Okay, I think that got most of what I wanted to get done there. These I can delete here. Exceptions is 8.1. And then we have, I'll go ahead and indent these. So it's going to be that. And then processes is next. System calls and process controller after that. Signals, my good old friend signals. Non-local jumps. Tools for manipulating processes. And finally summary. And then here we have 8.1, which is all these. So all of these we need to indent. So we'll do that now. That 8.1 goes here. 8.2 goes here. 8.4 goes here. 8.5 goes here. All right. So that's all of the 8. Table of contents. Let's write that out. Get status. Let's go back here. Get at all. Oh no. Sorry. I was in the right directory. Get at all. Get status. Looks okay to me. Let's go ahead and look through the diff. So we marked off of all of our linking stuff. We added in the exceptional control flow stuff. Marked that as complete. Changed a 1 to an I. And in here, just some makefile stuff, some C stuff, some problems. Cool. Get DC. I already did that. Get CI, we say finish. chapter 07. Get push all. And then I'm going to jump to learn log, get status here, get DC, get add all, get DC, get CI, add Frida to docs, reading, get push all. Okay, let's go back to CSAPP. And let's just see what our next lecture is. Exceptional control flow. So I think I need to take a break here and just chill for a little bit and then come back. Well, let's see how much time we have. I guess that's probably a better idea. So we got an hour and a half before I have to break for dinner. So maybe I just take a quick, short break here, and then come back and start in the lab. And what I'm going to commit to do is doing 5 minutes of work on the lab, and then after 5 minutes, I can do whatever I want. Whatever fun stuff I want, whether it's watching lectures or reading Soul of a New Machine or anything else. So that's what I'm going to commit to doing here. So I'm going to take a quick break. I'm not going to end the stream here. I'm just going to take a break, maybe about 5 minutes, and I'll be right back. Cool. Okay. All right. Let's start by just opening up the handout here. I got a little timer. I'm gonna time myself 5 minutes. All right. Close this. I'm gonna close that. And where's the handouts for these labs? They're under the labs repo. It's under cache. Okay. Oh, we got traces. Let's see, if we do ls traces. Okay. This is a handout directory for CSAPP Cache Lab. Let's go ahead and start. Before running the auto graders, compile your code, check the correctness of your simulator. So there's a test CSIM file here. You open a split, jump over to cache, test CSIM, yep. There's also test trans and a trace gen and a trans C. So check the correctness and performance of your transpose functions. Check everything at once. This is a program that your instructor runs, driver pi. Got some extra white space here for no good reason. Files, you will be modifying and handing in these two files, transpose function and a cache simulator CSIM. Tools for evaluating your simulator and transpose function. CSIM ref, test CSIM. Okay, let's go ahead and read the PDF. How many pages is this bad boy? 10 pages. I'm so tired. Today has been pretty low energy. I mean, I had a bit of a boost after lunch, after cardio. But, fuck, man. My energy is just super low. Alright. This lab will help you understand the impact that cache memories have on the performance of your C programs. The lab consists of two parts. In the first part, you will write a small C program, about 200 to 300 lines, that simulates the behavior of a cache memory. In the second part, you will optimize a small matrix transpose function, with the goal of minimizing the number of cache misses. Download the assignment. I've already done that. Thank you. Description. The lab has two parts. Part A, you will implement a cache simulator. Part B, you will write a matrix transpose function that is optimized for cache performance. Reference trace files. The traces subdirectory of the handout directory contains a collection of reference trace files that we will use to evaluate the correctness of the cache simulator you write in Part A. The trace files are generated by a Linux program called valgrind. For example, typing valgrind log fd1 tool lackey v trace mem yes ls-l. Let's try it. Lackey. Why is it doing all this dynamic stuff? Lackey, an example valgrind tool. Oh, that was my 5 minutes. Let's do another 5 minutes. On the command line runs the executive program ls-l, captures a trace of its memory accesses in the order they occur and prints them to standard out. Valgrind's memory traces have the following form: loaded, store, instruction, and I don't know what M is. Each line denotes one or two memory accesses. The format of each line is space, operation, address, size. The operation field denotes type memory access. I denotes instruction load. L is a data load. S is a data store. M is an M a data modify. How is that different than a store? I.e. a data load followed by a data store. There's never a space before each I. There's always a space before M, L, and S. The address field specifies a 64-bit hexadecimal memory address. The size field specifies the number of bytes accessed by the operation. Okay. Part A, writing a cache simulator. So that's going to be the main thing that I'm going to focus on tonight or today. It's only 3:40. Evaluation. Wow, most of it's part A, and then part B is here. But I didn't say what part B was, did it? Oh, programming rules for part B. So we have part A 4.2. There's 4.3. 4.3 part B, optimizing matrix transpose. Okay. Part A, you will write a cache simulator. Let's kill this guy. How do I turn this thing off? I needed more light here. There we go. There we go. I'm gonna turn the light on here. Alright. Part A, you will write a cache simulator in csim.c. It takes a Valgrind memory trace as input, simulates the hit misbehavior of a cache memory on this trace. I really don't want to do this. Alright. So it takes a Valgrind memory trace as input, simulates the hit miss behavior of a cache memory on this trace, and outputs the total number of hits, misses, and evictions. I mean, if you just gave me this prompt, I would have no idea how to do this. Like, just this first part. Obviously, they're going to give you more context and more information to help you get there. But, like, I guess the idea is that you can take an arbitrary program, run this Valgrind thing to trace all of its memory accesses, pipe that into your simulator, and then you get some type of picture of how many hits and misses it had, instead of asking the CPU itself, because I guess the CPU doesn't provide that information. Let's see. Let's ask the all-powerful, almighty AI gods. Does AMD 64 CPU, so I say do AMD 64 CPUs provide information on cache hit misses, hits, misses that are available for a given program? Okay, so perf. You can run perf. gperf, iperf, perf. Why simulate it when you can just run the fucking program and get the cache misses yourself? You can even use Valgrind as a cache simulator. Hmm. Let's open it up, CSIM. Oh, great. CacheLab.h. Ugh. I might just end the day here at 4. I don't feel like there's anything that I want to do that's productive. I have D&D tonight, so I got to get ready for that. And I got to eat dinner. I guess I could watch a lecture and veg out for an hour watching a lecture. Yeah, I might do that just so I don't burn the time, because otherwise I'm just going to be on YouTube or whatever, wasting time. So let's go to CSAPP repo, which was here, and go to video lectures, and we'll go down to exceptional control flow.
Welcome, good to see you. So today we're going to look at an idea called exceptional control flow. That's a very important part of making modern systems, and it exists at all levels of the system, from the lowest level hardware all the way up to software. So the idea is when you turn on a computer, from the very first time you turn it on, it just executes one instruction after another until you turn it off. Okay? And if you have multiple cores, then each of those cores are executing instructions one after the other. Now this sequence of instructions is called the control flow. Okay? And the actual sequence of instructions that the hardware is executing is called the physical control flow. Now normally this control flow that executes just one instruction after another, just sequentially in memory. And so far we've seen two mechanisms for altering the control flow so that we're not executing just the next instruction. So that's branches and jumps and procedure call and return. Okay. Now jumps and branches, jumps, call and return, those are reacting to changes in program state. So when you do a branch, you check the control condition codes, and then based on some the results of that comparison, then you do the branch. Okay. But a real system needs to be able to adapt to changes in the system state. Okay. So, for example, each core, if you have multiple cores, then each of those cores are executing instructions one after the other. Now, this sequence of instructions is called the control flow. Okay, and the actual sequence of instructions that the hardware is executing is called the physical control flow. Now, normally this control flow that executes just one instruction after another, just sequentially in memory. And so far we've seen two mechanisms for altering the control flow so that we're not executing just the next instruction. So that's branches and jumps, and procedure call and return. Okay. Now jumps and branches, jumps, call and return. Those are reacting to changes in program state. So when you do a branch, you check the control condition codes, and then based on the results of that comparison, then you do the branch. Okay. But a real system needs to be able to adapt to changes in the system state. Okay. So, for example, data arrives from a disk or a network. User types control C. Okay. The program executes an illegal instruction. Okay. All of these represent some kind of change in the system state, and we need some way to react to that. So what we need is, we call this exceptional control flow, because it's sort of outside of the normal control flow that we see in our programs. Now, exceptional control flow, or ECF, exists at all levels in the system. From the very lowest level hardware, at the very lowest level, we have what are called exceptions. And these are changes in the control flow in response to some low-level system event. So this is, and by event, we mean a change in the state. Now, exceptions are implemented using a combination of hardware and OS software, which we'll see in a minute. But these exceptional control flow exists at higher levels, too. So a process context switch is an example of exceptional control flow. It's implemented by hardware and the operating system kernel. And so a process context switch, as we'll see later today, you're executing your code in your current process, and then all of a sudden, the system is executing code from another process, right? So your process gets suspended, and so so that's a form of exceptional control flow where you're executing instructions within one process, and then all of a sudden you're executing instructions in another process. At a higher level, totally in software, we have the idea of a signal, and this is implemented by operating system software. We'll learn all about signals next lecture. And then at an even higher level, you have non-local jumps in C, which are just implemented by the C runtime library. So this allows you, non-local jumps allow you to break the normal call and return pattern. So from within a function, normally you can only return to the function that called you. Non-local jumps allow you to, within a function, break that and return to some other function or some other part of the code. So we'll look at signals and non-local jumps next lecture. Today we're going to look at exceptions and processes. So an exception is a transfer of control to the operating system's kernel, where the kernel is the memory resident part of the operating system. So an operating system provides all kinds of programs, like to list files, to change directories, to list the current processes. So all of that stuff constitutes the operating system. The kernel is the part of the operating system that's always resident in memory. So an exception is this really low-level transfer of control to the operating system because something happened in the system. So you're executing your code, user code, and then something happens, some event. So by event, we mean there's some change in the system state. In response to that, the exception transfers control from your user code to code in the kernel, which is called an exception handler. And then the kernel responds to that change in some way. This is called the exception processing. And then there's three things that can happen after the kernel handles the exception. It can return and re-execute the current instruction. Okay, and we'll see this is useful for things like page faults. Allows us to implement virtual memory. It could return to the next instruction, which I've shown here, or it could abort. Now, exceptions are implemented by hardware and software. So the actual transfer of control, the change in the program counter or IP, is done by the hardware. But the code that executes as a result of that exception is set up and determined by the operating system kernel. So every type of event has a unique exception number, which serves as an index into a jump table called an exception table. Okay. And so when event K happens, then the hardware uses K as an index into this table and gets the address of the exception handler for that exception. Okay. And so every time that event K happens, that handler K is invoked. Now, there's different kinds of exceptions. We distinguish them as being asynchronous or synchronous. Asynchronous exceptions happen as a result of changes in state that are occurred outside the outside of the processor. So these are called interrupts, and those changes in state are the processor is notified about those changes in state by setting a pin on the processor, an external pin called the interrupt pin. So this is the kind of happen as a result. When event K happens, implemented by hardware and software. So the actual transfer of control, the change in the program counter or IP is done by the hardware. It's implemented by. It could return to the next instruction, which could return to virtual memory, and we'll return instructions and return the exception to the processing. And then there's three things that can happen after the kernel handles the exception. It can return and re-execute the current instruction. Okay, and we'll see this is useful for things like page faults. Allows us to implement virtual memory. It could return to the next instruction, which I've shown here, or it could abort. Now, exceptions are implemented by hardware and software. So the actual transfer of control, the change in the program counter or IP is done by the hardware. But the code that executes as a result of that exception is set up and determined by the operating system kernel. So every type of event has a unique exception number, which serves as an index into a jump table called an exception table. Okay. And so when event K happens, then the hardware uses K as an index into this table and gets the address of the exception handler for that exception. Okay. And so every time that event K happens, that handler K is invoked. Now, there's different kinds of exceptions. We distinguish them as being asynchronous or synchronous. Asynchronous exceptions happen as a result of changes in state that are occurred outside of the processor. So these are called interrupts, and those changes in state are the processor is notified about those changes in state by setting a pin on the processor, an external pin called the interrupt pin. So this is the kind of when, say, a disk controller finishes doing a direct memory access and copying data from the disk into memory, it notifies the processor that it's finished that copy by setting the interrupt pin high. Okay. And so after an interrupt happens, the handler returns to the next instruction. So an interrupt typically it's as though you're running your program, and then there's like this little pause while the interrupt handler runs, and then your program just continues to run. Okay, so it's usually sort of done behind the scenes and doesn't affect your execution of your program. Now, the most common a common example of an interrupt is a timer interrupt. So all systems have a built-in timer that goes off every few milliseconds, and when the timer goes off, it sets the interrupt pin high, and there's a special exception number for timer interrupts. And we need this in order for we need this to allow the kernel to get control of the system again. Otherwise, a user program could just run forever in an infinite loop, and there'd be no way for the operating system to get control. So every few milliseconds, this timer goes off. That causes an exception into the kernel, and then the kernel can, as we see, the kernel can decide what to do. Maybe schedule a new process or let the current process run. And then an I/O interrupt from an external device is also a common example. Now, the other class of exceptions are synchronous exceptions, and there are three classes of those. One class is called a trap. A trap is a intentional exception. So this is an exception that's caused intentionally by the program. And the most common form of a trap is a system call. So the operating system kernel provides all kinds of services to a program, but your program doesn't have direct access. Your program can't call functions in the kernel. It can't access data directly in the kernel because that memory is protected and unavailable to user programs. So what the kernel does is it provides an interface that allows programs to make requests, to effectively call functions within the kernel and to make requests for various services. And this interface is called a system call. Okay, so a program makes a system call and requests various functions from the kernel. The kernel provides those, reacts to that request, and then returns control back to the function, or the calling program. So you can think of a system call as kind of, it looks like a function call, but it's really transferring control into the kernel. Okay, then there's, so traps are intentional. Faults are unintentional, but may be recoverable. Okay, so things like page faults, which we'll learn more about these when we study virtual memory, but something like a page fault, it's actually recoverable. It's just that the kernel it means that the data, the portion of the address space that your program referenced isn't actually in memory. It needs to be copied from disk where it's stored into memory, and then the instruction that caused the fault is just restarted, and then it works. The memory is there, and then the instruction works properly. But other faults are unintentional, unrecoverable, like protection faults. So if you try to access a portion of memory that's not allocated, or floating point exceptions, oftentimes those can be recoverable. So in either case, when there's a fault, it either re-executes the current instruction or it aborts. And then there's unintentional and unrecoverable exceptions, which are called aborts, and those always abort. So if you execute an illegal instruction, if there's a problem with your memory and it's corrupted, or if there's some problem with the machine, those create aborts that always that are unrecoverable and never return back to the program. Now, system calls, there's many different kinds of system calls, and they all have their own unique number, which is assigned by Linux. So for example, to read a file, there's a system call called read, which is number 0. Opening a file is system call number 2, and so on. And there's an instruction called syscall, which actually performs the system call. Now, you usually don't use the syscall instruction directly in your program. The Linux wraps those in system-level functions, which actually call it for you. But it's interesting to see how it actually works. So suppose you want to open a file. You call the system-level function called open with a file name and some options, say read only, write only. And so the syscall instruction takes the syscall number is in RAX, and then other arguments are in RDI, RSI, RDX, R10, R8, and R9. So you can see if we look in the open function, calls the __ open function, which actually invokes the syscall. So if you look at that code, you see it moves the 2, which is the syscall number for read, into EAX, and then it does the syscall. And then the syscall returns its status in RAX. If it's a negative number, then that means some error occurred. If it's a positive number, then that means that no error occurred. So in this case, in the open, it's returning a file descriptor, a small integer called a file descriptor, which then you can use in subsequent calls to read and write. And then you can see the code is checking for this negative return value, and there's a whole series of these compares. So let's look at an example of a fault. So here, suppose we have this program that we're writing into a valid region of memory, but it's not actually stored on. It's not actually in the memory. It needs to be loaded from disk into memory. So this is a so-called page fault. So this instruction, this movl, because the memory at this address isn't available, triggers a page fault. So that creates an exception, a transfer of control into the page fault handler in the kernel, which copies that page from disk to memory, and then it returns. And when it returns, it re-executes the movl instruction. So that's kind of cool. So now the memory is available, and now that this movl instruction, when it's re-executed, completes. And then we continue. Now, another type of fault is an invalid memory reference. So here we're accessing an element of A, which doesn't exist. It's an invalid reference. So in this case, the movl instruction, it looks like a page fault, but the kernel detects that it's an invalid address, that there isn't anything that can be loaded from disk. This is an invalid region of the virtual address space. So it sends a signal to the process, and then never returns. So the signal it sends is the infamous segmentation, the signal that causes the infamous segmentation fault message to print out. And we'll see next lecture. We'll see how these signals actually work. Okay, so we've seen exceptions are very low-level transfers of control that are implemented by both hardware and the operating system software. Because at the higher level is another form of exceptional control flow called, and we see it in the context of a process context switch. So let's look at what a process is. So a process, the idea of a process is one of the most fundamental and important ideas in computer science. And this classical definition is that a process is an instance of a running program. Okay, it's different from a program. A program can exist in many different places, right? A program exists in your as text in a C file. It can exist as the .text section of a binary. It can exist as bytes that have been loaded into memory. A process is an instance of a program that's running, that's in execution. And a process provides two key abstractions. Okay, the first abstraction is that it gives you the illusion that you have exclusive access to the CPU and the registers. Okay, so when you're running your program in a process, you never have to worry about any other programs modifying your registers, and you can't even tell that there's even other processes running on the system. Right? It looks except for occasional delays, like an instruction that just takes a little longer to run, except for that, it looks like you have unique, exclusive use of the processor and its registers. The other abstraction that it provides is the illusion that you have your own address space. Okay, so you have, and this is provided by a mechanism called virtual memory. So each running program has its own code, data, heap, stack, and you never see the code, and you never see the memory that's being used by other processes. Okay, so it looks, for all intents and purposes, the process gives you this illusion that you have access to exclusive access to all the memory and the processor. Now, the system runs many of these processes simultaneously. Even on a system with a single core, many of these multiple processes are actually running at the same time, concurrently. And you can see this if you look at this here I ran top on my Mac. And you can see it's running 123 total processes, 5 of which are actually running. And each one of these processes has its own unique process ID. This is integer. Now so it looks like you have unique access or exclusive access to the system. But in reality, suppose we have a single core, you're actually sharing the system, and the operating system is sort of managing that sharing. So what it does is we have a process that's running, and it has its own address space, and it has its own registers. And now at some point, at some point an exception occurs, either because of a timer interrupt or a fault of some kind or a trap. At some point, the operating system gets control of the system, and in this case, let's say it decides that it wants to run another process. So it copies the registers, the current register values into memory and saves them. And then it schedules the next process for execution, and it loads the registers that were saved from the last time that process was running. It loads those into the CPU registers, and then it switches the address space to the address space for this process. So the address space and the register values are the context, and so the context switch is the change in the address space and the registers. Okay. So then at that point, that process is running. Now in reality, on modern systems with multiple cores, the operating system will schedule processes on those multiple cores, and then if there's not enough cores to handle the processes, then it'll do the context switching just like we showed before. Now each process represents what we call a logical control flow. So if you were to, there's a physical control flow, which if we just looked at all the PC values, we'd be executing instructions from one process, and then all of a sudden we'd be executing from another process. But within a single process, there's a logical control flow, which are all the instructions for that process. Now, we say that 2 processes run concurrently if their flows overlap in time, otherwise they're sequential. So let's look at an example. We have 3 processes. Process A runs for a while, and then it's interrupted by process B and process C, and then eventually it continues running, and then it terminates. Process B interrupts process A, and then it runs for a while, and then it terminates. Process C, when process B finishes, then process C gets to run for a while. Then process A runs for a while, and then process C terminates. Okay, so given this definition of concurrency, which of these processes are running concurrently? What about A and B? Yes? So A and B's flows, B's flow overlaps with A's flow, right? So B finishes, starts and finish. This portion of B's flow overlaps with A's flow, right? Because B is still running, hasn't finished. Okay, so A and B are concurrent. And similarly, C and A overlap, so they're concurrent. But B and C are not concurrent, right? B finishes before C starts. Okay. Now, this idea of concurrency, this definition of concurrency holds regardless of the number of cores. Right? Even if you have one core, this example that I showed you was on one core. But even if you have multiple cores, as long as the flows overlap in time, they're concurrent. But we can think of these, no matter what, we can think of these as running in parallel with each other, at least from the point of view of these individual processes. Now, this notion of a context switch, it's managed by the kernel. Okay, and it's important to realize that the kernel is not like a separate process that's running. It always runs in the context of some existing process. And it's just code that's in the upper portion of the address space that gets executed as a result of an exception. So what happens, the way to think about this is that you have this process A that runs, and then an exception occurs which transfers control to the kernel. The kernel invokes its scheduler, which decides whether to let A continue to run or to to do a context switch and run a new process, another process. So in this example, the scheduler has decided to run process B, so it executes code and then sort of changes, sort of once it repoints the address space, then it's running in the context of process B, and it finishes loading the registers for process B, general purpose registers, and then transfers control to B, and B picks up where it left off. Okay. And then at some point another exception occurs, and the kernel decides to transfer control back to process A, which picks up where it left off right here. So whatever instruction, it finishes executing, whatever instruction it was executing at the time of the exception, executes the next instruction here. Now, Linux provides a number of functions that you can call from a user program to manipulate processes. And this act of manipulating processes we refer to as process control. Now, all of these functions, most of these functions invoke system, make system calls, but they're wrapped in higher levels, what we call system level functions that are the things you actually call from your user program. Now, Linux system level functions will typically return a -1 if there's an error. And then they'll set a global variable called error no to indicate the reason. So there's a hard and fast rule when you're invoking system level functions. You must check the return values from those functions. You should, and this you'll get into huge trouble if you neglect to check the return values. Okay, so you should never make a system level function call without checking the return value. And the only exception, there's some functions that return void, such as exit or free, don't return anything. So the typical way you would do this is like the fork call, which we use to create processes, returns the process ID of the process that it created, which is always positive. If there's an error, it returns -1. So we check for the return value to be less than 0, and then we deal with that error somehow. Okay. In this case, we're just printing a message and exiting. Now this gets, although it's essential to do this, it gets, from my point of view, where I'm trying to present code to you, it gets really messy. It takes up a lot of space. Yes?
Why are you returning here with a 0 instead of 1? Isn't this like an error?
I'm checking that it's less than 0.
No, I mean, you're returning with like a 0.
Oh yeah, that should be, normally the convention is to return non-zero. So you're right, it's not a hard and fast rule, but that's typically the convention. So yes, it should be exit 1. So what we'll do to simplify this in the code that we present to you and in the code that we present to you in the book, we'll define error reporting functions. So Unix style errors where the function returns -1 and then sets error no. If we get that kind of error, we'll print a message and we'll report what that error was before we exit. And so then in the code, we can replace that body of that if statement with just a single line. Okay, so that makes the code a little tighter. But we'll go even further than that, and we'll define these wrappers, which were pioneered by a great technical writer, W. Richard Stevens. And what we do here is we replace each function with a wrapper that has the identical interface as the function, the original function, and it has the first letter uppercase. And then what this wrapper does is it calls the original function, checks for the errors, and then if there's no error, returns what the original function would have returned. So the behavior of this wrapper is identical to the wrapped function if there's not an error. Okay, and if there is an error, then it deals with it somehow and prints a message. And so then this allows us to make our code really compact without violating this hard and fast rule that we have to check for errors. Okay, the simplest function, process control functions, are functions that allow you to get the PID for the current process, which is get PID, or the processor ID of the parent process that created the current process. Okay, so these take no arguments and they return an integer, which is a process ID. Now, Linux provides ways to create and terminate processes. And from a programmer's perspective, we can think of a process as being in one of 3 states. Running, so in this case, the process is actually running and execute instructions, or it can be scheduled. Maybe it's not running, but it can be scheduled at a later time. Right? And it's waiting to be scheduled. It can be stopped, which means that execution is suspended and won't be scheduled until further notice. So we'll see how this works when we study signals in the next lecture. But usually a process is stopped because it receives a certain kind of signal, and then the process becomes stopped and it won't be executed. It won't be scheduled until you explicitly tell it to be scheduled. Or a process can be terminated, which means it stopped permanently. Okay, so it'll never be scheduled again. It's done. Now, a process can be terminated for one of 3 reasons. So one, it receives a signal whose default action is to terminate it. Or your program returns from the main routine. So you can, if you know the definition for main is int, C main routines always return an int. So you can return from main, and that will terminate eventually it will terminate the process. Or you can explicitly call the exit function. The exit function exits the program with an exit status of its argument. So as you pointed out, the convention is for normal return is to return 0 and then non-zero on error. Or you can, another way to do this is just return an integer value from the main routine, and that will set the exit status. Now exit is kind of unusual, and you'll see this is typical of all these process control functions, that they normally functions you call them once, and then they return once. Okay, but exit you call once, and then it never returns. Okay, so that's a little unusual. Now a parent process can create a child process by calling the fork function. So fork takes no arguments, and it returns an integer. It creates a new child process, and then it returns in both the parent and the child. So this is a little hard to wrap your head around at first. It's called once by the parent, but then it returns in both. It creates a new process, and then it returns in both the parent and the child. And to the child, it returns 0. To the parent, it returns the child's process ID. Okay. The child gets an identical copy of the parent's virtual address space, but separate. Right? They're distinct, but immediately after the fork returns, the address space is identical. So that means that all the variables, all the global variables, the stack, the code, everything is identical in the child. It has exact same values as it does in the parent. The child gets identical copies of the parent's open file descriptors. So the child has access to any open files, including like standard in and standard out that the parent had. And the only difference is that the child gets a different process ID than the parent. So fork is really strange because it's called once, but returns twice, once in the parent and once in the child. So here's an example of this. This is an example program that has a local variable called x on the stack, initialized to 1. And then it calls fork, and fork creates the child and returns it returns a value to both the parent and the child. The only way we can distinguish whether we're executing in the parent or the child is to check that return value. Okay, so here, if the process ID, if PID is 0, then we're executing in the child. And remember, the child got exactly the same, has exactly the same memory and code as the parent. So x in the child is 1. So when we print this message from the child, we increment x and then print this message. So the child will print 1 plus 1, 2, and then exit. In the parent, when we check this process ID, it's going to be non-zero because it's the process ID of the child. So in this case, so the parent won't execute the body of this conditional. So the parent will execute this printf, and in the parent we decrement x before we print it. So the parent prints out 1 minus 1 is 0. Now, there's no guarantee. We have no guarantee whether the child or the parent execute first. It could, when the fork returns, the kernel may decide to schedule the child first. Okay, in which case this code in the body of the conditional would run, or it may decide to run the parent first. Okay, and there's no way to predict, and it's wrong. It's an error to make any assumption like that about what's going to run first, the parent or the child. And you can see that they share the same open files because both the parent and the child print to standard out, and it prints on the terminal. Okay, yes.
What if you call fork multiple times?
The question is, what if you call fork multiple times? I'll show you some examples of those. It gets a little hairy. We'll use a model called the process graph to sort of understand what happens. Okay, so just like you said, forks are kind of can be kind of complex to understand, especially if they're nested or you call them multiple times. So we use a tool called the process graph to capture sort of what could happen when we call forks. Right? We can't make any assumption about the ordering of different processes, but we can capture the partial ordering of events using this tool called a process graph. So what we'll do is we'll let each vertex correspond to the execution of a statement, and then an edge is the happens before relation. So A happens before B, and then we will label edges with current values of variables. If we have a printf vertices, a vertex that corresponds to a printf, we can label that with the output. And then every graph starts with a vertex with no in edges. So given this graph, then any topological sort of the graph represents some feasible total ordering of events. And by topological sort, we mean a total ordering of the vertices where all the edges go from left to right. Okay, so let's look at how this would work for our example program. Here we have the parent. Initially, x is equal to 1. And then the parent calls fork. The fork returns in both the parent and the child. The child prints, and both the parent and the child print the value of x after incrementing or decrementing, and then they both exit. Okay, so you can think of these as happening. So these happen concurrently, right, which means they can be interleaved in any way. So the topological sort of this graph will tell us what are feasible interleavings. Okay, so if we relabel the graph, just to keep it simple, so if we relabel these edges with just single letters, then this total ordering, A, B, E, C, F, D, represents it's a topological sort and thus a feasible total ordering. So here we have A executing, then B, then E executes in the child, and then at this point the kernel decides to swap out the child and now let the parent run. So the parent picks up and executes C, and then it gets rescheduled. Then the child gets scheduled and executes F, and then the parent runs and finally finishes. Right. So this is very unlikely that you'd only execute one instruction and then have a context switch, but it's feasible, right? Because because the total ordering is a topological ordering. On the other hand, this is infeasible because F here in this total ordering we're executing F before E, and you can see that that just can't happen, right? So the edges on the logical flow represented by this child have to occur in this order: first E and then F, right? Just because F follows E in the code, right? The compiler's not going to it's not going to alter those. Okay, so what happens if we have two consecutive forks? Well, let's draw the process graph will help us understand this. So in the parent, we print L0 and then fork, and that creates a child, and so the fork returns to this printf in both the parent and the child. So both the parent and the child print L1, and then both parent and child execute a fork. So that creates another child. That creates two children. Okay, and so that returns to the printf, which says bye. So the result of calling fork twice like this is that it creates 4 processes. Okay, and if it's confusing, you can always work it out with the process graph like this. Okay, so we can see feasible and infeasible orderings. So this one's feasible. Take my word for it. This one is infeasible, and let's see why. So at L0, and there's no way to print bye before the first fork, right? So that's infeasible. If we drew out this process graph, we'd have a backward edge. Okay, now what happens if we nest forks in the parent? Okay, I'm not sure why you'd want to do this, except maybe to torture 213 students, but so we can just work this out by drawing the process graph. So here we have the parent. It prints L0, and then it does a fork, so that creates a child. So the child, if fork is not equal to 0, then we're in the parent, right? So this code executes in the parent. If fork is 0, then we're executing the child, and the child just prints bye and then it eventually terminates. I didn't show it here, but it calls exit. The function that called this function calls exit. So the parent, so fork not equal to 0 indicates that this is the parent. So the parent prints L1, and then it does another fork. That fork creates a child. So if fork is not equal to 0, then we're in the parent. So the parent prints L2 and then exits this conditional and prints bye. If fork returns 0, then that means we're executing the child. So we don't execute this code. We jump out of this conditional, and then the child just prints bye. Okay? And we can so this represents an infeasible output from this program. L0 fork, so L0 followed by bye, that's feasible. And then followed by L1, that's OK. And then the next bye is OK, but we can't have this bye preceding this L2, right? Because L2 will this printf will execute before this printf. Okay, and I'll let you work out this one as an exercise. All right. Now, when a process terminates for whatever reason, the system actually keeps it around until it's reaped, and the reason until it's reaped by its parent. And the reason it does this is that the parent may want to know about the exit status of the child. So if a parent creates a child, it may want to wait for that child to finish and check its exit status. So when any process terminates, the system leaves it. It doesn't remove it entirely from the system. It keeps it a little bit of state associated with that child in the form of the exit status of the child and some other tables, some other OS tables. So because this child is terminated, but it's not gone, they're called zombies. So they're sort of half living, half dead. Right? And so a zombie remains a zombie until it's reaped by its parent using a function called wait or waitpid. And as a result of doing wait or waitpid, the parent is given the exit status information, and then the kernel deletes the zombie process. Now, what if the parent doesn't reap one of its child zombies? So if the parent terminates, then the system arranges for the very first process that existed in the system, called the init process, which has a process ID of 1. It arranges for the init process to reap that child. So orphan children will always be reaped by the init process. So we only really have to worry about reaping zombies in the case where we have long-running parents like shells or servers, right? Because in that case, a server may create millions of child processes. Each one of those child processes, when they terminate, become zombies and they have state, which takes up room in the kernel. So you can get this. It's a form of memory leak. If you don't reap these zombie children, that can eventually fill up the memory space and crash the kernel. So for cases where you have long-running programs, then we have to use wait or wait-pid to reap the children. So let's look at an example. First, let's look at an example of this zombie phenomenon. So here we have a function we call fork, and then within the child, we print a message, the process ID of that child, and then we exit the child. Within the parent, we print a message, and then we go into an infinite loop. Okay, so this is a parent that never reaps the child that it created. So if we run this program called forks, you can see it prints these two messages. The parent prints a message, and the child prints a message. And then, and we're running it in the background with this ampersand, because we're going to, otherwise it's still running, and we wouldn't be able to inspect it. So after we run this program in the background, then we use PS to print the current processes. And we can see that there's two. We can see here the parent, which is process ID 6639, and then the child, which is 6640, and the defunct indicates that it's a zombie. Okay, now if we kill 6639, that's the parent, and then do another PS, you see that the child is gone because it's been reaped by the init process 1. Okay. Now what happens if the child doesn't terminate? You might wonder, like if a parent creates a child, and then the parent, and then the child never terminates, and the parent terminates, then what would happen? Right? So let's look at an example of this and see. So here we're calling fork, we're creating a child. Within the child, we print a message, and then the child goes into an infinite loop. And the parent prints a message and then exits. So if we run this program, you can see that the two messages from parent and child. And then if we look at the processes, we can see that the child is still running. Okay, so the child process is still running even though the parent has terminated. And now if we kill this child, 6676, and then if we kill it, then we can see that it's gone, it's no longer in the system. Okay, so that child, when we killed it, that terminated it, it had no parent, so the init process reaped it, and it's no longer a zombie. So the function that we use to synchronize with children and reap them, the simplest one is called wait. And wait, it takes an optional status where you can get the exit status of inspect the exit status of the child. Basically, wait suspends the execution of the process that calls it until one of its children terminates. Okay, and it doesn't specify which one. It just waits until one of the children that it created terminates. And then if this child status is non-null, then the integer that it returns, or the integer that it points to, this is a pointer, the integer that it points to will be set to some value that indicated the reason the child terminated and its exit status. And you can check that using these macros, which your textbook describes in more detail. And I'll let you. So let's look at how this works in a simple example. So here we're calling fork and creating a child which prints a message and then exits. The parent prints a message, and then it waits for the child to terminate. And when the child terminates, it prints a message and indicating that the child terminated and then prints by. So if we were to look at the process graph for this, you would see that we would have the fork creates the parent and the child. Both the parent and the child do their printfs, and then the parent waits, it suspends until the child terminates, in this case by calling exit. Okay, so what that means is it's infeasible. So you can say hello from the parent. It's infeasible, though, for this child terminated message, CT, to occur before the by, right? Because the child hasn't yet terminated. So these two messages will never be printed until the child is terminated by calling exit. Okay. So is that clear? Yes? So the question is, can you have an output HP, HC, CT by? Yes. Yes, because the parent prints HP. There's a context switch. The child prints HC and then exits. And now the parent will, the weight will return, and then it prints CT by. Okay, this is a little more involved example. So here what we want to do, we're going to create a bunch of children, and then we're going to wait for them all to terminate. And we're going to wait, but we won't be able to wait in any specific order. Right? So here we have a loop, 0 through n, and in each loop body, we're going to fork a child and exit with a return status that's going to tell us which child it was. Okay. In the parent, so we do this n times, and then afterward, the parent inside a similar loop, 0 to n, waits for a child to terminate. So it'll wait for n children to terminate. Wait returns the process ID, and then a status, which is in this child status variable. And so we take that variable now, and we can use this wIfExited macro to determine if it terminated normally with an exit by calling exit. And if so, then we can check its exit status using the wExit status macro. Otherwise, if wIfExited is false, then that means something the child terminated for some other reason, not because it called exit. Okay, we can actually use wait PID, which is similar to wait, but it allows us to wait for a specific process, a specific child, a specific child with a specific process ID to terminate. And I'll let you, you can, wait PID is really involved, and it's described in detail in your textbook, and so you'll need to look there for the details of how that works. Now another important, so we've learned how to create new processes. But we haven't learned how to, when we call fork, we just create an exact copy of the child is just an exact copy of the parent, running the same code, same program, same variables. Okay, to run a different program inside of a process, we use a function called exec, VE. And exec loads and runs, within the current process, it loads and runs the executable file name, which is its first argument. And file name can be either a binary, executable binary, okay, or it can be a script. It can be a text file, a so-called script file that starts, whose first line starts with a pound, bang, and then the path of some interpreter. So for example, if you want to write a shell script, the first line of your shell script is pound, bang, and then the path name of the bash shell. And then that will execute bash, and then bash will read in the lines following and interpret them just as though you type them in at the command line. So in either case, it executes either an interpreter or it executes a binary with the argument list argv and a list of environment variables in envp. Okay, now by default, the first argument in argv is the name of the file that's being executed. So it's this file name. So what that allows you to do is, in your code, you can check argv0. If you want to print out the name of the file, the name of the program that's executing, you just print out argv0. Okay, now an exec overwrites all of the code and the data and the stack. It completely overwrites the virtual address space. So once you call exec within a process, it blows away the current program. That's it. Okay. However, it retains it's still the same process. It's just running now a different program. And so it retains the process ID and any open files that you have. So exec is really mind-blowing because it's called once, but it never returns. Okay. Except if there's an error. So if this file doesn't exist, for example, then exec will return -1. But otherwise, in normal operation, it never returns. All right, so let's look at the structure of the stack when this new program starts. So after the exec VE finishes its work, it creates a new stack. It loads in new code and data, creates a new empty heap. Okay, everything's new. And the stack that it creates has the following form. Okay, at the bottom, here's the bottom of the stack, and our stack is growing this way. So the first function that executes is a function called libc_start_main. So that has a stack frame. So let's look. This is what I'm showing here is the situation right before the startup code calls main. Okay. So there's the future stack frame for main will be here at the top of this, following the top of the stack. There's some padding, and then the argument list in argv is contained on the stack. So the argv is a list of pointers terminated by the null pointer, and each one of these pointers points up into a string that corresponds to an argument. Okay, so when you run a program, you specify the program name, and then arguments separated by spaces. Okay. And so these arguments, this argv is a list of pointers to those argument strings. And it's pointed to, right as main is called, it's the second argument to main, so it's contained in RSI, the address of this argument list. The number of arguments is contained, is the first argument, argc, and that's contained in RDI by the x86-64 parameter passing convention. Now the environment list is also contained on the stack, and it too consists of a list of pointers, each of which points into an environment string, which is a set of key equal value pairs. Okay? And it's pointed to by the global environment variable environ, and if it's passed in, it's pointed at in EMVP, which is contained in RDX, which is always holds the third argument. Okay, so let's look now how we would use this. So we want to, within our current program, we want to execute the ls command with two arguments, -lt and /user/include. So what this is saying is list the files in /user include, show the long form of the listing, and sort them in time order from most recently used to least recently used. So the way we do this, if we just called exec_ve, it'd blow away our program. So assuming we want to continue to do work after we execute ls, the standard way to do this is to create a child using fork, and then exec within the child, right? Have the child do the work, and then the child terminates, and the parent maybe will wait for the child, maybe not, right? Usually we'll wait for the child. So within the parent, we fork a child, check that it's 0, and so if it's 0, then we're executing, this code executes within the child. So the child does the exec. It passes the name of the function, since the name of the function that we want to, the program that we want to execute is always contained in the first element of argv. We call exec with a parameter of myargv0, and we've set up the argument list in myargv, and we pass the global environment variable environ. We're just going to use the current list of environment variables that we have in the parent. Okay, and these environment variables are things of the form user equals row, current working directory. And so if this program in myargv0 doesn't exist, then exec will return -1. So we check for that condition and then exit. Otherwise, it never returns, right? It executes ls. The code for ls, this is the name of a binary. This is /bin/ls is a binary file. That binary file gets loaded into memory. That code gets executed, and it terminates. Okay, so the child, at this point, after the exec, the child is running the ls code, and it's no longer running any of this code. Now this seems, the first time you see this combination of fork and exec, it seems a little odd, doesn't it? Why not just have one command that creates a new process and runs a program in that process? Why separate? Why have these two separate fork and exec? I mean, in fact, Windows does this. Windows has like one command that creates a process and executes it. But it turns out that having a separate function like fork just to create processes is actually really useful. I mean, sometimes you just want to create replicas of your current process. For example, let's say you have a server, and you want to create a concurrent server. You want to create multiple copies of that server, then you just fork a bunch. You have the parent server can fork a bunch of children. So that's useful. They're just all running the same code. But what this also allows you to do is it allows you to execute code in the child before you call exec. So you may want to set some like some signal. This is especially useful when you're dealing with things like signals. If you want to block certain signals or unblock certain signals, you can do it right here in this gap between the fork and the exec. Okay, so that's it. So just to summarize what we've talked about today, exceptions are in response to events that require some kind of non-standard or exceptional, what we call exceptional control flow. They can be generated internally in the form of interrupts or internally in the form of traps and faults. So at any point in time, a system has multiple processes, only one of which can execute on a single core. So the process execution is interleaved by the kernel. And each process thinks that it has sort of total control of the processor and its address space. There's only one mechanism to spawn processes, that's fork, and it's called once and returns twice. We can terminate a process by calling exit, which is called once and never returns. We reap and wait for processes using wait or waitpid, and we load and run programs using exec_ve or one of its variants. And this one is called once and normally never returns. Okay, so that's it for today, and we'll see you. Have a good weekend, and we'll see you on Tuesday.
All right, I'm gonna hop off here, get some dinner, call it a day. And I'll be on tomorrow. I guess I should work on the lab, but I might also do some of the Linux binary analysis book. Now that we've gotten through linking, or the chapter on linking here, I feel like the Linux binary analysis stuff I'm a little bit more eager to approach. So, yeah, I'll be on tomorrow, either for Linux binary analysis or the cache lab, which, to be honest, I'm not super eager to to work on that thing. But yeah, I'll be on tomorrow after the gym. Cool. All right, see ya.